Hi, I'm Martin Kiefer. Welcome to this video on our research paper Scotch, generating FPGA accelerators for sketching at line rate. Let's get right into it. The term sketches is used in various connotations. For now, think of helpful little screen summaries like count-min, AGMS, or hyperlog-log, and in a couple of slides I will give you a concise definition of what we consider sketches. These sketches are used in various applications, ranging from approximate query processing to machine learning and large-scale networking. FPGAs are an architecture that allows us to create custom hardware by using software. Think of uncommitted hardware resources that sit on a chip, and by using software we can reprogram and rewire these resources. One of the benefits of custom hardware is that we are very flexible in the types of parallelism we can use. We can use data, task, and pipeline parallelism with very little overhead. This is what makes sketches and FPGAs such a good combination, because we can use this parallelism to create accelerators with high guaranteed throughput. Let me give you a sneak peek into our evaluation to support this point. Here we see implementations of a count-min sketch on a state-of-the-art FPGA, GPU, and CPU compared in terms of throughput. What you see is that we get a 1.4x increased throughput when comparing to a GPU, and compared to the CPU, we even get an increase of 14x. If implemented properly, that throughput is guaranteed and independent of the data distribution. By using hardware, we can also save a couple of watts in terms of power consumption, as we only create circuits that are actually needed to create the sketch. In this experiment, we see that we get a 2.4 to 2.9x reduction in power draw. With these two very good reasons to use FPGAs for sketching, now let's see what it takes to achieve these improvements. The main challenge when implementing sketching on an FPGA is that one has to be an FPGA expert to do so. Scotch's approach to overcome this is to abstract and automate as much of the development process as possible. First, the implementation is device, vendor, and interconnect specific. The expert must take that into account, and any change to the setup requires non-trivial adjustments. Scotch overcomes this by being device and I/O agnostic. That means all algorithm-specific parts of the implementation work independent of the setup. Next, the expert has to program register transfer level, which is the common abstraction to describe hardware. However, it requires a software developer to think in terms of unfamiliar concepts like registers, clocks, and signals. Furthermore, auxiliary components like memory management must be implemented that are provided when programming software. Scotch overcomes this by providing lightweight mechanisms to specify the algorithm. From this specification of the algorithm, the entire sketching RTL is generated automatically. Finally, the implementation has to be hand-tuned. We definitely want the sketch summary to be as large as possible to get the best accuracy. However, we have to make sure that the implementation stays within the resource limits of the FPGA, and it has to satisfy timing to function correctly and to achieve the desired throughput. This requires the expert to perform trial and error tuning. She has to compile the implementation with different sketch sizes, with compile times being in the order of hours. Scotch approaches this challenge by providing an algorithm that performs this tuning automatically. To see how Scotch reaches device and I/O agnosticism, it is interesting to look at a high-level overview of the accelerators generated. They consist of two components. The first one is the sketching unit, and it is generated and optimized by Scotch. It contains all the hardware that is required to create the sketch. The second one is an I/O controller that is responsible for moving in data from the outside and passing it to the sketching unit. Furthermore, it is responsible to expose the state of the sketch summary to the outside world. This hardware is highly specific to the device and interconnect used, thus the I/O controller has to be provided by an expert. However, I/O controllers can be used and reused for different algorithms and for different projects. Next, let's look at a high-level overview of the Scotch system itself. First, we have the RTL generator. It takes a description of the sketch and parameters, in particular the size of the sketch, and then it generates the sketching unit. The sketching unit is integrated into an FPGA design project that contains the I/O controller, and then everything is compiled using the toolchain provided by the FPGA vendor. From this, we get a compilation report and a bit stream. From the compilation report, we learn how many FPGA resources were used and whether timing was satisfied. The bit stream is the program to initialize the FPGA. To optimize the summary size, an autotune component repeatedly calls the RTL generator with various sketch sizes and analyzes the compilation report. If the autotune algorithm finds an implementation it deems optimal, it returns the sketch size and the bit stream. Next, we discuss how sketches are described in Scotch. Scotch assumes sketches that are generalized by the select update model. The state of the sketch is a matrix with a given number of rows and columns. For each input value, we first evaluate a select function. The select function determines which entry in each row is going to be updated. The update is determined by an update function. If you're familiar, for example, with the count-min sketch, this may feel pretty familiar to you, but the model also generalizes other sketches like AGMS, fast AGMS, or min hashing. The select update model is the foundation for Scotch DSL. It is a domain-specific language to specify the select and update function. It uses bit vectors as first-class citizens, which makes sense given that FPGAs do not assume byte-sized data types, and neither do the mathematical formulations of the algorithms. The language supports logic and arithmetic operations, plus restricted control flow. We do not allow constructs that would result in an accelerator that would not provide guaranteed data rates. And most importantly, we do not expose clocks or control signals, so software developers can provide these functions without worrying too much about the hardware that is being generated. Here's an example of a Scotch DSL update function. It depends on a random seed, the input value, the previous state, and it assigns the new state. Next, let's look at the automated tuning of the summary size. The automated tuning algorithm expects the parameter space to look as follows. With the optimization parameter, be it the number of rows or the number of columns, resource consumption increases. In our case, the key resources are elementary logic units and blockram elements. If the optimization parameter is chosen sufficiently small, compilation succeeds. If the optimization parameter is increased further, at some point timing fails, and eventually the resources on the FPGA are exceeded. In this space, we essentially perform binary search for the optimal value, which is the largest value of the parameter space for which compilation succeeds. Next, let me show you a small subset of our evaluation. In this experiment, we are building a count-min sketch with 32 rows, while the number of columns is optimized by the autotune algorithm. We compare in terms of throughput to a state-of-the-art GPU and CPU implementation. Let's look at the results. We were able to find an implementation with 130,000 columns, and when comparing to the Xeon CPU, we find that we are able to outperform it by roughly a factor of 5, while when comparing to the GeForce GPU, we are outperformed by roughly a factor of 3. The reason for this is that the GPU implementation exploits data parallelism aggressively, while the FPGA-Accelerator only consumes one input value per clock cycle. If we replicate resources to consume 4 input values per clock cycle, things look a little different. Now we're able to outperform the GPU because throughput has increased by a factor of 4. However, the number of columns of the accelerator has decreased by a similar factor, as we need more resources to implement columns due to replication. If we take this further to an implementation that consumes 16 elements per clock cycle, we are even able to achieve more than 200 gigabits per second throughput. The takeaway message is that first, data parallelism is crucial for high throughput, and second, there is a trade-off between throughput and the summary size. To summarize, Scotch is a system to generate FPGA-based sketching accelerators. It mainly consists of 3 components, which are Scotch DSL, the RTL generator, and the autotune algorithm. What you get from using Scotch is high guaranteed throughput at low power consumption, which one would expect from an FPGA accelerator. But we can get all of that without an FPGA expert in the loop. Scotch is publicly available on GitHub, and if you're interested in further details on Scotch, there are plenty in the paper. In particular, there are details on the sketching unit, data parallelism, as well as an extensive evaluation. Stay safe and enjoy this year's VLDB. Thank you.